Schweinfurt, Germany, August 17, 1943, 1300 hours, and Oberstleutnant Johannes Steinhoff, commanding Jagdgeschwader 27, watched his Messerschmitt Bf 109 G6 fighters struggling to reach the American B-17 Flying Fortress bombers cruising at 27,000 feet, their Daimler-Benz DB 605 engines wheezing and gasping on B4 fuel with its mere 87 octane rating, when suddenly 4 silver P-51 Mustangs dropped from 32,000 feet with a speed and aggression that made his blood run cold, their Packard-built Merlin engines screaming with a sound he'd never heard before, powered by something the German chemical engineers at IG Farben and the synthetic fuel plants at Leuna had dismissed as impossible to mass-produce. That mythical 130 octane fuel that would transform every assumption about aerial combat and reveal that Germany's 4-year plan had catastrophically miscalculated the one element that mattered more than aircraft design, more than pilot training, more than production numbers, the chemistry of the fuel itself. The story of how high-octane aviation fuel became the Luftwaffe's invisible enemy begins not in the skies over Germany but in the boardrooms and laboratories where German engineers, including Nobel laureate Friedrich Bergius himself, had pioneered the very chemistry that would defeat them, having developed the Bergius process for converting coal to synthetic fuel as early as 1913, a process that could theoretically produce any octane rating desired if only Germany had possessed the vast petroleum infrastructure, the rare materials for tetraethyl lead production, and most critically, the industrial freedom from Allied bombing that the Americans enjoyed in their massive refinery complexes spreading from Pennsylvania to Texas to Louisiana, where Eugene Houdry's revolutionary catalytic cracking process was transforming crude oil into liquid gold at 77 separate facilities by 1944. Major Gunther Rahl of JG-52, who would survive the war with 275 aerial victories, later confessed in Allied interrogation that German fighter pilots had noticed something profoundly disturbing during the Battle of Britain that no one in the Reichsluftfahrtministerium wanted to acknowledge. The British Hurricanes and Spitfires they had easily outclimbed and outrun during the Battle of France just months earlier had somehow transformed into entirely different machines, climbing faster, diving more aggressively, and maintaining speeds at altitude that should have been aerodynamically impossible for their engine specifications. A mystery that wouldn't be fully understood until captured RAF pilots under interrogation kept mentioning something called 100-octane fuel that arrived in massive tanker convoys from America. The mathematics of octane ratings meant nothing to the average Luftwaffe pilot trying to intercept a B-17 formation, but to the German chemical engineers at companies like IG Farben and Brabag, who had spent decades perfecting the Fischer-Tropsch process and the Bergius hydrogenation method to convert Germany's abundant coal reserves into aviation fuel. The implications were devastating and undeniable, because octane rating directly determined how much pressure an engine could generate before the fuel detonated prematurely, and while German B4 fuel with its 87 octane rating limited the Daimler-Benz DB 601 and DB 605 engines to manifold pressures around 1.42 atmospheres, the Allied 130 fuel allowed Rolls-Royce Merlins and Allison engines to operate at manifold pressures reaching 70 inches of mercury, nearly double what German engines could sustain. Hermann Göring, the corpulent Reichsmarshal who commanded the Luftwaffe, had been warned as early as 1938 by his own technical staff that Germany's synthetic fuel program, despite its impressive production volumes that would reach 124,000 barrels per day by early 1944, could never match the octane ratings achieved by natural petroleum refined with tetraethyl lead additives. But Göring, intoxicated by the early victories in Poland and France where German fighters had dominated with superior tactics and experienced pilots, dismissed these concerns with his characteristic bombast, declaring that German pilots and German engineering would overcome any mere chemical disadvantage, a delusion that would cost thousands of Luftwaffe pilots their lives. The Japanese perspective on this fuel crisis was even more desperate as Admiral Takejiro Onishi, architect of the kamikaze program, would later admit that Japan entered the war with aviation fuel that never exceeded 87/91 octane and ended it with the same pathetic mixture, forced to watch American Hellcats, Corsairs, and Mustangs literally fly circles around the Mitsubishi Zero and even the late-war Nakajima Ki-84 Hay-8, which when tested post-war by Americans using 140-octane fuel suddenly demonstrated performance equal to any Allied fighter, proving that Japanese aircraft designers had created competitive airframes and engines that were crippled by what pilots called peasant fuel, derived from pine root oil and whatever synthetic processes the Japanese could manage with their strangled resources. In Italy, the situation proved equally catastrophic, as General Giuseppe Santoro of the Regia Aeronautica discovered, when his pilots flying the Macchi C-202 Folgore, considered Italy's finest fighter and powered by a license-built German Daimler-Benz DB 601 engine, found themselves completely outclassed by American P-47 Thunderbolts and British Spitfire Mark IXs over Sicily in 1943. Not because of inferior aircraft design, Mario Castoldi's sleek Folgore was aerodynamically superior to many Allied designs, but because Italian refineries could barely produce 87-octane fuel, forcing pilots to watch helplessly as Allied fighters climbed above them, dove through their formations with impunity, and escaped at speeds the Folgore could never match despite its theoretical capabilities. The secret history of how America developed this war-winning fuel advantage begins with a French mechanical engineer named Eugene-Jules Houdry, who had served as a tank officer in World War I, and became obsessed with finding a way to convert coal into gasoline, eventually emigrating to America in 1930, where he partnered with Sun Oil Company and Saucony Vacuum to develop a revolutionary catalytic cracking process that could transform heavy crude oil into high-octane gasoline at a fraction of the cost of traditional thermal cracking, a process so efficient that by 1937 the first commercial Houdry unit at Marcus Hook, Pennsylvania was producing gasoline with octane ratings that German chemists had declared economically impossible. The Houdry process worked by passing vaporized petroleum over a silica-alumina catalyst at temperatures around 450 degrees Celsius, breaking the long hydrocarbon chains into smaller, more volatile molecules with naturally high-octane ratings, then adding precisely measured amounts of tetraethyl lead, that miraculous and toxic compound discovered by Thomas Midgley Jr. at General Motors, to boost the octane rating even further, creating fuel that could withstand compression ratios and manifold pressures that would cause German synthetic fuel to detonate catastrophically, destroying engines in seconds. Jimmy Doolittle, the famous aviator who would later lead the raid on Tokyo, had been hired by Shell Oil in 1930 specifically to develop high-octane aviation fuels, and his relentless advocacy convinced the United States Army Air Forces to standardize on 100-octane fuel in 1938, a decision that required building an entirely new refinery infrastructure but would prove to be one of the most important strategic decisions of the war, because it meant that every American fighter and bomber engine could be designed from the outset to exploit the higher compression ratios and manifold pressures that 100-octane fuel enabled. By contrast, Germany's synthetic fuel program, despite its impressive scale with plants at Leuna, Bohlen, Zeitz, Magdeburg, and 20 other locations, remained trapped by fundamental chemistry problems that no amount of German engineering brilliance could overcome, because the Fischer-Tropsch process that converted coal to liquid fuel produced hydrocarbons with naturally low octane ratings around 40-50, requiring massive amounts of additional processing and additives to reach even the modest 87 octane of B4 fuel, while the Bergius direct hydrogenation process could theoretically produce higher octane fuel but required enormous quantities of hydrogen, elaborate high-pressure equipment, and most critically aromatics like benzene and toluene that were also desperately needed for explosives production. The German C3 fuel, their highest-grade aviation gasoline with ratings of 95/120 octane that was reserved for specialized fighter units, required such expensive production methods and rare materials that it never constituted more than 30% of aviation fuel production, forcing most Luftwaffe squadrons to operate on B4 fuel that left them at a devastating disadvantage, particularly at high altitudes where the thin air exacerbated the performance gap between German and Allied engines, creating what Luftwaffe pilots called the death zone, above 20,000 feet where American escort fighters ruled supreme. Adolf Galland, the famous German ace who rose to command the Luftwaffe fighter force, recognized this crisis earlier than most when he famously told Göring in September 1940, during a tense meeting at Carenhall, "I would like an outfit of Spitfires for my squadron," a statement that infuriated the Reichsmarschall but revealed Galland's understanding that British fighters possessed some advantage beyond their elliptical wings and skilled pilots, an advantage he wouldn't fully comprehend until 1943 when captured Allied technical documents revealed the truth about 100/130 octane fuel and its transformation of engine performance. The first major combat demonstration of this fuel advantage occurred during the Battle of Britain, when RAF Fighter Command, having received its first shipments of American 100-octane fuel in March 1940, suddenly found its Hurricanes and Spitfires capable of performance that shocked both British test pilots and German opponents, with climb rates increasing by 500 to 1,000 feet per minute, speeds jumping by 25 to 34 miles per hour at crucial combat altitudes, and most importantly, the ability to maintain maximum power for extended periods without engine damage, allowing British pilots to pursue German bombers and fighters with an aggression that had been impossible with 87-octane fuel. The transformation was so dramatic that Air Chief Marshal Hugh Dowding initially worried that British pilots hadn't been properly trained to exploit their aircraft's newfound capabilities, ordering special courses at operational training units to teach pilots how to manage the higher manifold pressures and temperatures that 100-octane fuel permitted, while simultaneously keeping the fuel's properties classified at the highest levels, creating cover stories about new propeller designs and improved superchargers to mask the true source of the RAF's enhanced performance. Meanwhile, in the Pacific Theater, Japanese naval aviators flying the Mitsubishi A6M0 from carriers like Akagi and Kaga discovered to their horror that American F-6F Hellcats and F-4U Corsairs could simply climb above them and attack from positions the Zero could never reach, despite the Zero's legendary maneuverability and lightweight, because Japanese engines running on 87-octane fuel couldn't generate enough power at altitude to compete with American Pratt & Whitney R2800 double Wasps. Running on 130-octane fuel and producing 2,000 horsepower with manifold pressures the Japanese considered impossible. Lieutenant Commander Saburo Sakai, Japan's legendary ace with 64 victories, would later write that Japanese pilots knew something was fundamentally wrong with their fuel when they examined crashed American fighters and found engines with compression ratios that should have destroyed themselves in minutes with Japanese fuel, leading to desperate experiments with methanol injection, water injection, and even nitrous oxide systems to try to match American performance, all while Japanese petroleum engineers at the Naval Technical Arsenal in Yokosuka worked frantically to improve their fuel quality, hampered by Japan's lack of petroleum resources and the American submarine campaign that was strangling oil shipments from the Dutch East Indies. The Italian tragedy unfolded in the skies over North Africa, where pilots of the Regia Aeronautica flying Macchi C-200 Zetas and C-202 Falgors discovered that their aircraft, which performed beautifully in test flights and aerobatic displays, became flying coffins when facing American P-40 Warhawks and British Hurricanes running on high-octane fuel, with Italian ace Franco Bordoni Bisleri reporting that enemy fighters seemed to possess engines with twice the power of Italian machines, able to break off combat at will by simply climbing away at angles the Macchi fighters couldn't match. The mathematics of this disadvantage were brutal and unforgiving. Every 10-point increase in octane rating translated roughly to a 3% increase in possible manifold pressure, which meant a 7 to 10% increase in horsepower, so an aircraft running on 100-octane fuel versus one on 87-octane enjoyed approximately a 30% power advantage, enough to turn an evenly matched dogfight into a one-sided slaughter, particularly when combined with the superior high-altitude performance that high-octane fuel enabled through higher supercharger boost pressures. German engineers at Daimler-Benz and BMW desperately tried to compensate for their fuel disadvantage through increasingly complex mechanical solutions, including methanol water injection systems, MW50, nitrous oxide injection, GM1, and ever more sophisticated supercharger designs, but these systems added weight, complexity, and maintenance burdens to aircraft already struggling with Germany's deteriorating industrial situation, while doing nothing to address the fundamental problem that German fuel simply couldn't support the manifold pressures and compression ratios that Allied engines took for granted. The Focke-Wulf FW-190, designed by Kurt Tank as Germany's answer to the Spitfire, exemplified this crisis when its BMW 801 radial engine, despite its sophisticated fuel injection system and impressive 1,700 horsepower rating on C3 fuel, found itself completely outclassed by the American P-51 Mustang, whose Packard Merlin engine could sustain 1,695 horsepower on standard 100-130 fuel and surge to over 1,790 horsepower on the 110-150 grade fuel introduced in 1944, all while operating at altitudes where the BMW 801 was gasping for air and hemorrhaging power. The crisis deepened catastrophically when the United States Army Air Forces began Operation Point Blank, the combined bomber offensive against Germany, in June 1943, sending formations of B-17 Flying Fortresses and B-24 Liberators escorted by P-47 Thunderbolts and later P-51 Mustangs deep into German airspace, where Luftwaffe fighters discovered that even when they managed to reach bomber altitude, Their engines running on 87-octane fuel couldn't generate enough speed to catch the bombers before. The escort fighters, climbing from below with their 130-octane advantage, pounced on them like hawks on pigeons. The testimony of captured German pilots told a consistent story of frustration and rage, watching American fighters perform impossible maneuvers, climbing when German fighters had to dive, accelerating when German engines were at maximum power, and most gallingly, escorting bombers all the way from England to Berlin and back, a range that German fighters could never achieve because their low-octane fuel required richer mixtures and higher consumption rates to avoid detonation, limiting their endurance to a fraction of what Allied fighters could achieve. Major Wilhelm Balthasar of JG2, before his death in 1941, had warned the Luftwaffe High Command that something fundamental had changed in British fighter performance during the Battle of Britain, submitting detailed combat reports showing that RAF fighters were achieving climb rates and speeds that violated everything German intelligence knew about the Hurricane and Spitfire designs, but his warnings were dismissed as excuses for the Luftwaffe's failure to achieve air superiority, with Göring particularly contemptuous of any suggestion that German technology might be inferior. The Japanese military attaché in Berlin, Colonel Takeo Ito, reported to Tokyo in 1943 that German engineers had privately admitted their synthetic fuel program had failed to achieve the octane ratings necessary for competitive fighter performance, recommending that Japan attempt to acquire American refining technology through neutral countries, a desperate suggestion that revealed how completely the Axis powers had been outmaneuvered in the chemistry of warfare, reduced to hoping for industrial espionage to acquire what American companies were producing in massive quantities. By early 1944, the Hudry process and its variants were operating in 77 plants across the United States, producing not just 100/130-octane fuel but experimental batches of 115/145 grade fuel that would allow American fighters to operate at manifold pressures approaching 90 inches of mercury, power levels that would have instantaneously destroyed any German or Japanese engine, while the Fischer-Tropsch and Bergius plants in Germany struggled to maintain production under increasingly heavy Allied bombing, their workforce decimated and their raw materials disrupted. The oil campaign that began on May 12, 1944, with the first systematic bombing of German synthetic fuel plants, targeted precisely this vulnerability, with the 8th Air Force and RAF Bomber Command focusing on the massive Leuna works, the Brabag plants at Bolin and Zeitz, and the hydrogenation facilities at Politz, understanding that destroying Germany's ability to produce even low-grade aviation fuel would ground the Luftwaffe more effectively than shooting down individual fighters. Strategic insight that would see 18,328 tons of bombs dropped on Leuna alone in 22 separate raids. Friedrich Bergius himself, the Nobel laureate whose process had promised to give Germany independence from imported oil, watched in horror as his life's work became a strategic liability. His plants at Leuna requiring 350,000 forced laborers under the Geilenberg Special Staff just to maintain minimal production after Allied bombing, while American refineries operated in complete safety, their Hudry units running 24 hours a day to produce the fuel that was slowly strangling the Third Reich. The testimony of Albert Speer, Hitler's Minister of Armaments, revealed that by September 1944, German aviation fuel production had fallen to 10,000 tons per month, compared to 180,000 tons in April, forcing the Luftwaffe to ground training flights, cancel offensive operations, and ultimately reduce its once mighty fighter force to a handful of elite units flying on carefully hoarded C-3 fuel, while American fighters roamed German skies at will, their engines singing the song of 100 of 130 octane. Superiority. In Japan, the situation had become so desperate by 1945 that the Imperial Navy was experimenting with pine root oil, sake brewing byproducts, and even turpentine as aviation fuel additives, while Nakajima and Mitsubishi engineers designed new engines like the HAM-R that could theoretically compete with American power plants but were crippled by fuel that pre-detonated at compression ratios American engines considered routine, forcing Japanese pilots into increasingly desperate tactics including ramming attacks and finally kamikaze missions when conventional combat became impossible. The story of Sergeant Satoshi Anabuki of the 50th Sentai, who scored 39 victories flying a Nakajima Ki-43 Hayabusa, illustrates the Japanese tragedy perfectly. Despite his exceptional skill and bravery, he reported that American P-38 Lightnings could simply climb away from combat whenever threatened, their turbo-supercharged Allison engines running on high-octane fuel achieving performance at 30,000 feet that his Hayabusa couldn't match at 20,000, forcing him to rely on ambush tactics and the enemy's mistakes rather than the aggressive energy fighting that American pilots employed with their fuel advantage. The Italian collapse came even faster, with the Regia Aeronautica essentially ceasing to exist as an effective fighting force by mid-1943, not because Italian pilots lacked courage or skill. Aces like Franco Lucchini and Adriano Visconti proved Italian pilots could compete with anyone, but because their Macchi and Fiat fighters, running on fuel that barely qualified as aviation grade, couldn't protect Italian cities from American B-24 Liberators cruising at altitudes Italian fighters needed 10 minutes to reach, by which time the bombers had dropped their loads and turned for home. The supreme irony was that Germany possessed the scientific knowledge to produce high-octane fuel, with IG Farben chemists fully understanding the relationship between molecular structure and octane rating, the role of aromatics like toluene and xylene, and even the manufacturing process for tetraethyl lead, which Karl Bosch had actually helped develop before the war, but the industrial infrastructure required to produce these additives at scale, particularly the lead alkyls and aromatic compounds, competed directly with explosives production and other critical war materials, forcing impossible choices that always favored immediate needs over long-term aviation fuel quality. Dr. Walter Reppe of IG Farben, who had pioneered acetylene chemistry that could theoretically produce high-octane fuel components, found his research subordinated to synthetic rubber production after Germany lost access to natural rubber supplies, while his American counterpart Vladimir Ipatiev, working safely at Universal Oil Products in Illinois, developed new alkylation processes that boosted American fuel octane ratings even higher, widening the gap between Allied and Axis aircraft performance with each passing month. The combat reports from late 1944 make for grim reading from the German perspective, with Luftwaffe pilots describing American fighters that seemed to operate under different laws of physics, climbing vertically for thousands of feet, accelerating in level flight when German fighters were diving, and maintaining combat power for entire missions while German engines, stressed beyond their design limits trying to compensate for inferior fuel, suffered catastrophic failures with increasing frequency, connecting rods punching through crankcases and cylinders seizing from detonation damage. General Lieutenant Adolf Galland's final report as General of Fighters, submitted in January 1945 before his dismissal, stated bluntly that the Luftwaffe faced not a crisis of aircraft or pilots, but a crisis of chemistry, arguing that Germany's failure to develop high-octane fuel production had effectively lost the air war before it began, a conclusion that so enraged Göring that he accused Galland of defeatism and treason, though every technical expert who reviewed the report agreed with its conclusions. The Japanese Navy's final analysis, discovered after the surrender, calculated that American carriers could launch and recover aircraft 40% faster than Japanese carriers simply because American aircraft, with their high-octane fuel advantage, needed shorter takeoff runs and could climb more steeply after launch, while Japanese aircraft required every foot of flight deck and favorable wind conditions just to get airborne with useful combat loads, a disadvantage that proved fatal at battles like the Philippine Sea, where American fighters slaughtered Japanese aircraft in what became known as the Marianas Turkey Shoot. Commander Minoru Genda, architect of the Pearl Harbor attack, admitted after the war that Japan had known about America's fuel advantage from intelligence reports but had assumed it was propaganda, unable to believe that fuel chemistry could provide such dramatic performance gains until captured American aircraft were tested with actual 100-octane fuel, revealing that Japanese engines had been designed correctly but were being strangled by what he called coolies' fuel that belonged in farm tractors, not fighter aircraft. The Italian assessment was even more damning, with General Giuseppe Santoro writing that Italy had entered the war with biplanes and ended it with biplanes, not because Italian designers couldn't create modern aircraft. The Macchi C205 Veltro and Fiat G55 Centauro were world-class designs, but because Italian fuel quality meant these aircraft could never achieve their design performance, forcing pilots to fight with one hand tied behind our backs while the enemy used both fists, a metaphor that captured the frustration of an air force destroyed not by enemy action but by petroleum chemistry. Meanwhile, American production of 100/130 octane fuel had reached such massive scales that the United States could afford to be wasteful, with ground crews at forward airfields in the Pacific reportedly using high-octane aviation fuel to clean parts and even burn trash, While German pilots were measuring their fuel in liters and Japanese pilots were draining the tanks of crashed aircraft hoping to find a few gallons of usable gasoline. A disparity that spoke to the fundamental industrial mismatch between the Allied and Axis powers. The development of 115-145 grade fuel in 1944, tested initially in modified P-38 Lightnings and P-47 Thunderbolts at Wright Field, Ohio, pushed American engine performance to levels that seemed like science fiction to Axis engineers, with manifold pressures reaching 90 inches of mercury and power outputs exceeding 2,800 horsepower from engines that had been designed for 2,000, all achieved through nothing more exotic than improved refining processes and carefully calibrated tetraethyl lead. Additives that American chemical companies had mastered through decades of automotive fuel research. The Rolls-Royce engineers at Derby and the Packard engineers in Detroit, working from the same Merlin design, discovered they could extract different power levels simply by adjusting their engines for different fuel grades, with the British typically conservative in their boost pressures while Americans pushed their engines harder, confident in their fuel quality and their ability to replace worn engines, a luxury German and Japanese forces could never afford as their industrial base crumbled under Allied bombing. The story of the Nakajima Ki-84 perfectly encapsulates the Axis tragedy. When examples captured in the Philippines were tested at Clark Field with American 140-octane fuel instead of the 87-octane Japanese fuel, they suddenly demonstrated performance equal to P-51 Mustangs, climbing to 20,000 feet in 5 minutes 54 seconds compared to over 9 minutes on Japanese fuel, proving that Japanese engineers had designed a world-class fighter that was crippled from birth by fuel that turned it into a mediocre also ran, a discovery that brought several Japanese engineers to tears when they learned of it after the war. The German Messerschmitt Me-262 jet fighter, which Hitler hoped would restore air superiority through revolutionary turbine technology, ironically used J-2 fuel that was essentially kerosene with an octane rating irrelevant to turbine operation, finally escaping the octane trap that had strangled piston-engine Luftwaffe fighters, but arriving too late and in too few numbers to matter, while American jets under development used the same high-quality kerosene that American refineries could produce in unlimited quantities from their advanced catalytic cracking processes. The human cost of this chemical disadvantage was catastrophic for Axis pilots, who found themselves fighting brave but ultimately doomed battles against an enemy whose engines gave them every advantage: altitude, speed, acceleration, range, and endurance, while their own engines, starved of proper fuel, could only deliver a fraction of their design performance, turning what should have been even contests into one-sided slaughters that decimated the experienced pilot cadres of all three Axis air forces. Lieutenant Hans Joachim Marseille, the legendary Star of Africa, who scored 158 victories against the RAF in North Africa, reportedly told his crew chief that he could feel his Bf 109's engine struggling above 20,000 feet, like a horse trying to run in sand. While his opponents seemed to gain strength with altitude, their engines singing smoothly on their superior fuel, while his DB605 coughed and stuttered on the 87-octane B4 fuel that was all the Afrika Korps could obtain, a disadvantage that would eventually contribute to his death when his engine failed in September 1942. The Japanese ace Tetsuzo Iwamoto, who survived the war with 80 victories, described the frustration of watching B-29 Superfortresses cruise overhead at 30,000 feet, knowing his Ki-84 could theoretically reach that altitude but that his engine, gasping on 87-octane fuel, would take so long to climb that the bombers would be gone before he could engage, forcing him to wait for lower flying targets while Tokyo burned beneath streams of bombers he couldn't touch. Italian ace Sergeant Maggiore Terezio Martinoli, flying a Macchi C-205 Veltro over Sicily in 1943, reported that American P-47 Thunderbolts would actually toy with Italian fighters, climbing just out of reach and then diving through formations repeatedly, knowing the Italian fighters couldn't pursue them either up or down, their engines limited by fuel that pre-detonated at the manifold pressures necessary for combat maneuvering, reducing proud fighter pilots to the role of target drones for American gunnery practice. The production statistics tell the complete story of this chemical warfare. By 1945, the United States was producing 359,000 barrels per day of 100/130-octane aviation fuel from a combination of Houdry catalytic cracking, alkylation, and thermal reforming processes, while Germany's entire synthetic fuel production had collapsed to less than 1,000 tons per month. Japan was mixing pine oil with alcohol in desperate attempts to keep aircraft flying, and Italy had ceased to exist as a military power, its air force grounded not by lack of aircraft but by lack of fuel to make them combat-worthy. The post-war United States Strategic Bombing Survey concluded that the Allied fuel advantage had been worth approximately 500 additional fighters in every major air battle, calculating that the performance differential provided by 100/130 octane fuel versus 87 octane fuel translated into a 3:1 combat advantage when all factors were considered: climb rate, speed, altitude capability, and endurance, a margin that no amount of pilot skill or tactical innovation could overcome. Dr. Heinrich Nordhoff, who would later run Volkswagen but worked for Opel during the war, testified that German automotive engineers had known since 1936 that American refining technology was a generation ahead of German synthetic fuel processes. But their warnings were ignored by Nazi leadership, who believed political will could overcome chemical reality, a delusion that cost thousands of German pilots their lives and ultimately contributed to the Third Reich's defeat. The final irony came when Soviet forces captured the Leuna synthetic fuel complex in April 1945, finding elaborate German equipment that could produce every type of fuel except the high-octane aviation gasoline that might have saved the Luftwaffe, with German chemists explaining that they had known how to make 100-octane fuel but lacked the tetraethyl lead, the aromatics, and most crucially, the safe production facilities that American refineries took for granted, having been forced to disperse and camouflage their operations to survive Allied bombing. The Japanese surrender brought equally bitter revelations, with Admiral Takejiro Onishi writing in his final letter before his suicide that Japan had been defeated not by atomic bombs or Soviet invasion but by the chemistry of petroleum, arguing that Japan's inability to produce high-octane fuel had doomed every military operation from Midway onward, forcing Japanese forces to fight with bamboo spears against steel swords, his metaphor for the technological mismatch created by fuel quality. The Italian Air Force's final report, prepared by General Mario Agmonicat, calculated that the Regia Aeronautica had lost approximately 70% of its air battles not through pilot error or tactical mistakes, but through simple inability to engage enemy aircraft operating at altitudes and speeds that Italian fuel quality made impossible, concluding that Italy had entered an industrial war with artisanal technology, hoping that courage could compensate for chemistry, a hope that proved tragically misplaced. Eugene Houdry himself, decorated by the French government after the war for his contribution to Allied victory, reflected that his catalytic cracking process had been developed for purely commercial reasons in the 1930s, with no thought of military application, but had accidentally provided the technological foundation for Allied air superiority, proving that in modern warfare, the laboratory could be as decisive as the battlefield, and that the chemistry of fuel mattered more than the courage of pilots. The legacy of this chemical victory extended far beyond World War II, with American refineries continuing to produce high-octane aviation fuel for the Korean War, where F-86 Sabres running on 115-145 grade fuel dominated MiG-15s despite the Soviet jets' theoretical performance advantages, proving again that fuel quality could determine air superiority, while the synthetic fuel technology developed by Germany found new life in South Africa's Sasol plants, using Fischer-Tropsch processes to produce fuel from coal during the apartheid era's oil embargo. The human dimension of this story emerges most clearly in the testimonies of surviving pilots from all sides, who described the gradual realization that they were fighting not just enemy pilots but enemy chemistry, that their aircraft were being defeated not by superior tactics or training but by molecular structures and octane ratings, reducing aerial combat from a contest of skill and courage to a predetermined outcome based on refinery technology, a realization that broke the spirit of many Axis pilots long before their aircraft were shot down. Major Johannes Steinhoff, who we met in our opening scene and who survived the war to become commander of the West German Air Force in the 1960s, wrote in his memoirs that the most bitter moment of his combat career came not when he was shot down and burned in a Mi-262 crash, but when he learned after the war that American fighters had been using fuel that gave them a 30% power advantage, meaning that every combat he had fought had been rigged from the start, like playing chess where the enemy's pieces could move twice for every move we made. Commander Saburo Sakai, Japan's great ace who we encountered earlier, spent his post-war years studying petroleum chemistry, trying to understand how Japan had been so completely blindsided by American fuel technology, concluding that Japan's military leadership had been so focused on spiritual factors like pilot courage and tactical innovation that they had ignored the mundane but crucial science of octane ratings, a failure he compared to training the finest swordsmen in the world and then giving them wooden swords to fight enemies with steel. The story reached its ultimate conclusion when test pilot Eric Brown, flying captured Axis aircraft for the Royal Navy, systematically tested German, Japanese, and Italian fighters with both their original low-octane fuel and high-octane allied fuel, documenting performance improvements of 30–40% across every parameter: speed, climb, ceiling, and range, proving definitively that the Axis had fielded competitive aircraft crippled by inferior fuel, a finding that vindicated the deceased designers and pilots who had been blamed for their Air Force's failures. The production infrastructure that enabled this American advantage was staggering in scale, with Standard Oil, Shell, Texaco, and dozens of smaller companies operating refineries that covered thousands of acres, employed hundreds of thousands of workers, and consumed vast quantities of crude oil from Texas, Oklahoma, California, and Venezuela, all protected by two oceans from enemy attack. While German synthetic fuel plants operated under constant threat of bombing, Japanese refineries depended on vulnerable tanker routes, and Italian facilities barely functioned at all. The technological details of the Hudry process that made this victory possible deserve recognition. The silica-alumina catalyst that cracked heavy hydrocarbons at relatively low temperatures, the precise temperature control that prevented coking, the regeneration system that burned carbon deposits off the catalyst, and the fractionation towers that separated the resulting products into different octane grades, all innovations that seemed mundane compared to radar or atomic bombs but proved equally decisive in determining the war's outcome. The tetraethyl lead story adds another layer of irony, as this compound, now banned worldwide for its environmental toxicity, provided the crucial octane boost that helped win World War II, with American chemical companies producing thousands of tons of this poisonous additive while German plants, despite having the technology, couldn't produce it at scale because they lacked the raw materials and secure facilities, forcing them to use inferior additives or accept lower octane ratings. Disadvantage that accumulated with every gallon of fuel burned. The German methanol water injection system, MW-50, that equipped late-war Bf-109s and FW-190s represented a desperate attempt to compensate for fuel disadvantage through mechanical complexity, injecting a 50–50 mixture of methanol and water into the engine to prevent detonation at higher boost pressures. But this system added weight, reduced reliability, and could only be used for minutes at a time, while American fighters simply opened their throttles and let their 100–130 octane fuel deliver sustained power throughout entire combat missions. The Japanese attempt to compensate through aircraft design produced remarkable innovations like the Zero's exceptional range achieved through lean fuel mixtures and lightweight construction. But these advantages evaporated when facing American fighters that could simply climb above the Zero's ceiling and attack from positions the Japanese couldn't reach, proving that no amount of design brilliance could overcome the fundamental limitation of 87 octane fuel in a world where enemies were using 100 octane or better. The Italian tragedy was perhaps most poignant because Italy had produced genuinely excellent aircraft designs like the Macchi C-205 Veltro and Reggian Re 2005 Sagittario that could have competed with any Allied fighter if properly fueled, but instead became examples of wasted potential, their beautiful airframes and sophisticated engines reduced to second-rate performers by fuel that belonged in agricultural equipment, not combat aircraft, a mismatch that Italian pilots recognized but could do nothing about. The strategic bombing campaign against German synthetic fuel production, particularly the concentrated attacks on Leuna beginning May 12, 1944, demonstrated Allied understanding of this vulnerability, with 6,552 bomber sorties dropping 18,328 tons of bombs on this single facility, accepting heavy losses including 119 aircraft in 3 raids that failed to hit the target, because destroying German fuel production was worth any price, a calculation that proved correct when the Luftwaffe essentially ceased to exist as an effective force by early 1945. The human cost of these raids was staggering on both sides, with 1,280 American airmen lost attacking Leuna alone, while the Germans employed 350,000 forced laborers under horrific conditions trying to repair the damage and maintain production, a desperate struggle that ultimately failed when the combination of bombing damage and raw material shortages reduced German aviation fuel production to less than 1% of its peak capacity by March 1945, grounding most of the Luftwaffe and leaving German skies defenseless. The parallel Japanese experience saw the Imperial Navy's carefully hoarded aviation fuel reserves, built up over years of preparation, exhausted in a series of carrier battles where American fighters, climbing faster and higher on their superior fuel, achieved kill ratios that reached 10-1 by late 1944, forcing the Japanese to adopt kamikaze tactics not from cultural preference but from mathematical necessity, as conventional combat had become impossible when enemy fighters enjoyed such overwhelming performance advantages. The post-war analysis by the United States Strategic Bombing Survey, which examined captured German documents and interviewed hundreds of German officials and engineers, concluded that Germany had lost the air war before it began by failing to recognize the crucial importance of fuel chemistry, investing billions of Reichsmarks in aircraft production while neglecting the fuel technology that would make those aircraft competitive, a strategic blindness that reflected Nazi ideology's preference for visible achievements over invisible chemistry. Dr. Karl Krach, chairman of IG Farben's supervisory board and Göring's plenipotentiary for chemical production, testified at Nuremberg that he had repeatedly warned Nazi leadership about the fuel-octane gap, but had been told that German pilots' superior training would compensate for any technical disadvantage, a delusion that persisted even as Luftwaffe losses mounted and American bombers ranged deeper into German airspace, protected by fighters whose engines gave them every advantage in combat. The Japanese testimony was equally revealing, with Captain Mitsuo Fukuda, who led the Pearl Harbor attack, admitting that the Imperial Navy had known about American fuel advantages from intelligence reports but had dismissed them as propaganda, unable to believe that the Americans had achieved such a technological lead in what seemed like mundane petroleum chemistry, a failure of imagination that contributed to Japan's catastrophic defeat in the air war over the Pacific. The final missions of the war demonstrated the ultimate triumph of chemistry over courage, as American B-29s cruised over Japan at altitudes no Japanese fighter could effectively reach. Their right are 3350 engines purring smoothly on high-octane fuel, while below them Japanese pilots in stripped-down fighters, burning the last drops of inferior fuel mixed with pine oil and alcohol, attempted futile interception missions that ended in failure or suicide attacks, the last desperate acts of an air force defeated by octane ratings. The German Me-262 jet fighter, which finally escaped the octane trap by using turbine engines that ran on kerosene, arrived too late and in too few numbers to matter, with only about 1,400 built compared to over 15,000 P-51 Mustangs, proving that revolutionary technology couldn't overcome industrial disadvantage, especially when that revolution came after the war was essentially decided, with German cities in ruins and synthetic fuel plants destroyed beyond repair. The survivors' accounts paint a picture of gradual realization and growing despair as Axis pilots understood their predicament, with German ace Erich Hartmann, history's highest-scoring fighter ace with 352 victories, admitting that by 1944 he was avoiding combat with American fighters whenever possible, knowing that their performance advantage made engagement suicidal unless he could achieve complete surprise, a tactical limitation that reduced the Luftwaffe from hunters to hunted, always looking over their shoulders for the inevitable bounce from above. The economic dimension of this chemical victory was staggering, with the United States spending approximately $20 billion in modern dollars on refinery infrastructure and fuel production during the war, an investment that paid dividends not just in military victory but in post-war prosperity as these facilities converted to civilian production, while Germany's synthetic fuel plants, those that survived bombing, were mostly dismantled or abandoned, their elaborate Fischer-Tropsch and Bergius process equipment now museum pieces commemorating a failed attempt to achieve independence from petroleum geology. The environmental legacy of this fuel war persists today in contaminated soil around former synthetic fuel plants, where decades of coal processing and chemical production left toxic residues that still require remediation, while the tetraethyl lead that gave Allied fuel its octane advantage contaminated millions of acres around airfields worldwide. A poisonous victory that would take generations to clean up, proving that even winning technologies carry hidden costs that outlast the conflicts they help win. The technological evolution continued after 1945, with turbojet engines eliminating the octane problem entirely by using kerosene-based fuels that didn't require anti-knock properties, while automotive engines gradually increased compression ratios as peacetime fuel quality improved, using technologies developed for aviation fuel to improve civilian transportation, a transfer of military technology to civilian use that characterized much of the post-war economic boom in America and Europe. The Korean War proved that the lessons of fuel quality hadn't been forgotten, as American F-86 Sabres using 115/145 grade fuel dominated Chinese and North Korean MiG-15s despite the Soviet jets' superior climb rate and ceiling, with American pilots reporting they could overcome the MiG's advantages through careful energy management enabled by their superior fuel, proving that even in the jet age, fuel quality remained a crucial factor in air combat effectiveness.